Let's run through about 5 quick-ish examples of substitution with indefinite integrals, starting with the integral of e to the x cosine e to the x dx. Now, if you think about this really hard and maybe try and fiddle around a little bit, you might be able to work out an antiderivative of this, finding a function which, when we take the derivative, comes out to this. For some of you, it might not take very long, in fact. But working towards a method that allows us to integrate more complex functions with as little work as possible. Let's think about applying the substitution rule here. As a general rule of thumb, the two main occasions when we want to try substitution are when we have a composition of functions, when we have one function inside of another, as we do here, we have a cosine of an exponential. And in that case, we'll usually try letting the inner function be a variable like u. And the other place is when we see a function and its derivative floating around. So we have cosine, its derivative is sine, we don't see that anywhere. But we also have an e to the x that shows up twice. And the derivative of e to the x is itself, so we have a function and its derivative. So both of those are checked off here. So this looks very promising for a substitution problem. There are other places where we use substitution as well, but those are the most common occasions. So what I usually do for these is just kind of come off to the side someplace. And we pick some variable. U is the most common choice, but any variable that's not in use is fine. And we let that equal some portion of this. Like I said, this e to the x being inside of a cosine is a good thing to try. So we let u be e to the x. Now we consider what the differential of this would be. If u is equal to e to the x, then the differential du is e to the x dx, right? Since the derivative of e to the x is itself. So now if we come back to this original integral, and let's rearrange this just a little bit. We have cosine of e to the x. There's also this factor of e to the x, but e to the x times dx is what we're looking for here. So let me write this, instead of putting the e to the x up front, I'll move it to be afterward. So we can write this as cosine e to the x times e to the x dx. And now with this substitution here, we see that we can write e to the x is equal to u. So this is cosine u. E to the x dx is equal to du. So we have the integral of cosine u du. Now this is something we can integrate. You know the antiderivative of this. The antiderivative of cosine is sine. So we have sine u plus a constant, right? But we made up the variable u. The original problem was in terms of x, not u. So we need to put that back in. We have the sine of what was u. U was e to the x. So this is the sine of e to the x plus a constant. In general, when you do an integration problem, finding an antiderivative of anything that is more, more complicated than a single little function, it's probably a good idea to check this. You can differentiate this. You can take the derivative with respect to x of the sine of e to the x plus a constant. And this is with the derivative of sine as cosine. So we have cosine e to the x, but then chain rule tells us we have to multiply by the derivative of what's inside. Derivative of e to the x is e to the x. Derivative of a constant is 0. So this is e to the x cosine e to the x. And that is exactly what we started with, e to the x cosine e to the x. So we have this here. I might sometimes separate that so it doesn't look like it's part of our chain of equality or anything like that. Right. So this is kind of an illustration of the general technique. One of the simpler uses of this. Do note that anytime you take an antiderivative, remember to add that constant as soon as you evaluate that, because the antiderivative is equal to some member of a family of functions. You don't want to say it's equal to just a single function. Do not just do a bunch of work and then slip in the plus c at the end. Even if that gives you the right result at the end, you will have written incorrect equations along the way. And for some of the work that you're doing later, that will be a problem, actually, especially in differential equations. The constants that are involved come into play much earlier, so you need to make sure to bring those in as soon as they appear. But this is the basic idea. Now this one was very nice. It happened to be exactly what we needed it to be. Frequently, we are not so lucky. Let's take a look at this example. We have the integral of x squared e to the x cubed dx. Now again, we have a composition of functions. There's a cubing function inside of an exponential function. So this suggests allowing u to be x cubed, the thing inside of that. Then the differential du, the differential of x cubed is 3x squared dx. Now you'll notice looking at this that we don't have 3x squared dx. We have a dx, we have an x squared, but there's no 3. So we need to be careful how we handle this. There are lots of different ways of handling the bookkeeping. I'll run through 3 of them, I think, here, actually. They're all equivalent, it's just some people prefer to think about it in different ways. One approach you can take is to manipulate the original integral to force it into the precise form that we need. We need a 3x squared dx. We only have x squared dx. So we can say, all right, we need a 3. Let's introduce that by multiplying by a fancy 1 that looks like 1/3 times 3. 1/3 times 3 is 1, so I can bring this in without changing anything. Right? And then if I rearrange things a little bit, we can pull the 1/3 out front. We have 1/3 of the integral of e to the x cubed times 3x squared dx. Go ahead and separate that here. So we have 1/3 of the integral of e to the power of, now x cubed is what we're calling u. 3x squared dx is equal to du. So we have 1/3 of the integral of e to the u du. That is e to the u plus a constant. I'm going to call this constant c1 because I've written this very precisely with the 1/3 and whatnot. But now let's go ahead and do a few things at once. Let's multiply the 1/3 in. So we have 1/3 e to the power of, again, u is a variable we made up. We want to write this back in terms of x. So we get x cubed there. Plus, now 1/3 of this constant c1 is another constant, a third c1, let's just call that c. And now we have that expression there. Again, I was being fairly precise with these brackets. Because of how this works with constants, in practice we will often not do that. I would just write 1/3 e to the u plus the constant c, kind of implicitly distributing that 1/3 through to get our final constant. That usually works fine unless things get complicated. But just want to show this once to illustrate what's going on there so you can see what's happening. So this is one way of handling this. If you don't have the right constants, you can do a little bit of manipulation to force the constant you want, and that usually brings in another fraction that you can pop out. Any of you physics fans can think of this as like a virtual particle pair, but if you don't know what that means, don't worry about it. Now that was one way of handling the bookkeeping. Like I said, there are others. Let's put this over here. So let's come back to this. We have the integral of x squared e to the x cubed dx. We still want to do the same substitution where we let u equal x cubed. And then the differential du is equal to 3x squared dx. So that all starts off the same. Another approach that some students take when they see that it doesn't perfectly match this, some students will algebraically solve for the differential dx. If du equals 3x squared dx, we can divide 3x squared on both sides. So we have du divided by 3x squared equals dx. Okay? And then what they'll do is to come to this integral and say, all right, Let's substitute the things that we know. We have an integral of x squared. Does x squared match anything? Not quite. We'll leave it alone. We have e to the x cubed. Well, x cubed is equal to u, so we'll replace x cubed with u. And we have dx. dx is equal to du divided by 3x squared. So we can do those replacements and then start simplifying. We have a division by 3. We can pull that out front as a 1/3. This x squared and that x squared divided by x squared is 1, so those basically cancel, and we're left with an e to the u du. And then the rest of this works out the same, right? A third e to the u plus a constant, so that is 1/3 e to the x cubed plus a constant. So that's another way of handling the bookkeeping. It tends to be a little bit of extra writing compared to some of the others, especially if this gets a little bit larger and messier. But some students like that because you substitute a couple things in, and then you just algebraically simplify. Kind of grind through that. It's a little bit more systematic. There's a third approach, and this is the one that I personally tend to use most. Let me recopy this once more. We have the integral of x squared e to the x cubed dx. The approach that I tend to use is kind of somewhere in between these two. So what I would do personally on this problem starts off the same way. We let u equal x cubed. Du equals 3x squared dx. And I would look at this and say, okay, what do we have and what do we not have? We have the x squared and the dx, but we don't have the 3. So we need to get the 3 away from the x squared dx. Let's divide both sides by 3, and I would write that 1/3 du is equal to x squared dx. So then when we do these substitutions, I see that I'm introducing, well, let's write it this way. I would usually skip this step, but let's make it as clear as possible. We have an integral. We have e to the x cubed, that's e to the u. There's an x squared dx, and x squared together with dx is equal to 1/3 du. Okay, these two things together give us this thing right here. So, and again, usually I would just, rather than writing that, I would pull the 1/3 up front. But if you do write it out, to be careful, then you can do that in your next step, that moment of simplification. And then again, the rest proceeds as before. These are, very minor differences in bookkeeping and just sort of a few points along a spectrum. You can find sort of whatever works best for you in terms of how you prefer to keep track of things. These are a few examples. I will probably be sticking with things like this for most of the rest of my work because this is just what's natural to me. And it's also kind of a midpoint between things. So hopefully from there, if you prefer kind of one extreme or the other, you can at least still adapt from there. You'll note that in every case, the first two steps were the same, right? I didn't change what I substituted. In this particular problem, there is one obvious substitution, that's u equals x cubed. And the first thing we do with that is to find the differential du equals 3x squared dx. That was exactly the same in every one of these three versions. U equals x cubed, du equals 3x squared dx. U equals x cubed, du equals 3x squared dx. Those are all the same. It's just a matter of how you personally want to keep track of the bookkeeping. If you don't even need to really do the bookkeeping, because honestly with simpler things like this, these days I don't even usually write this last step. I just think, oh, I need to divide that 3 over. I write the 1/3 up front. If you practice with these enough, you can do that, whatever. It's all a matter of making sure that you find a way that you can keep track of what all the factors and coefficients are and what gets taken care of where. So experiment with these, try some different examples, figure out what works best for you. Let's look at another example. We have the integral of 3t plus 2 to the power of 2.4. This again is a composite function. We have some function raised to a power. So we have a linear function inside of a power function. So our common standard technique is to set a variable equal to the inner function. U equals 3t plus 2. du here, taking the derivative of this, would give us 3 dt. So there's our differential. And we have, actually I just realized I broke my own rule because I was going to show you how these would work. We don't have a 3 floating around on the outside, so let me go ahead and divide that out. So we have a 1/3 du equals dt. So just to make that a little bit more explicit. Now we can come back to this integral and say, all right, we've got a 1/3 going on here. dt is replaced with a 1/3 du. So I'll have 1/3 of some stuff du. 3t plus 2 is equal to u. So we have u to the power of 2.4. So after these substitutions, we get 1/3 the integral of u to the 2.4 du. Taking the antiderivative of that, we add 1 to the exponent using the power rule. So that is 3.4 over 3.4 plus a constant. So we have u to the power of 3.4 divided by 3 times 3.4. So we get 9, 1.2 looks like 10.2 plus a constant. And again, u is a variable that I made up. We need to switch back to what we were given, which was t. U is equal to 3t plus 2. So we have 3t plus 2 raised to the power of 3.4 divided by 10.2 plus a constant. There's our antiderivative there. So hopefully you can kind of see what's going on there and get the hang of that. Let's look at, I believe this is exercise number 18 from the textbook. The integral of z squared over z cubed plus 1 dz. Now, looking at this, you might not really see a composition of functions, but we do see there's a function and its derivative, or at least up to a scalar multiple, a constant multiple, I should say, a scaling factor. There we go. Scaling factor or constant multiple. If we look at this denominator, z cubed plus 1, I'll go ahead and write that. Its derivative, the derivative of z cubed is 3z squared, right? So the differential of z cubed plus 1 is 3z squared dz. And we basically see that derivative here. Again, not without the 3, but, or not with the 3, but we have the z squared. The constant factor doesn't really matter. I just realized that I've had a bunch of 3's here. That's not quite ideal. I should probably change these later. Sorry we keep getting these 1/3, but that's just sort of what happens in these. There's nothing special about the 1/3. This is just purely coincidence. I hope it doesn't bother you too much. But we see that we have z squared dz is equal to 1/3 du. So I can put the du up here, the 1/3 out front, and z cubed plus 1 is u, right? Now we can integrate this. We have 1 over u du. The antiderivative of 1 over u is the natural log of the absolute value of u. So we have a constant there. So we have 1/3 the natural log of the absolute value of z cubed plus 1. I'll give that 1 some serif so it doesn't look like the absolute value bars, plus a constant. This type of structure happens frequently enough that we often think of the denominator as being the inside of a reciprocal function. So even though this isn't really a composition of functions in the usual sense, a common technique, like if you aren't sure where to start, try letting u equal the denominator. That doesn't always work, but like maybe 80% of the time, right? There are a lot of times that fails, but more often than not, if you have a fraction like this, letting u be the denominator and seeing what you get is, worth a try. Substitution is sometimes kind of an art, so be okay with failing on your first attempt. When you have an integral to work with and you want to try substitution, or even without substitution, whatever you're trying to do, maybe you do algebraic manipulation first, whatever it is, you can try something, try manipulating algebraically or try a substitution or whatever, see what it does. If that doesn't work, just cross it out, try something else, right? Even those of us who are very experienced with integrals, sometimes we get one where the first thing we try simply doesn't work, and we have to go back to the drawing board and try a different technique. These kind of get messy. There isn't a single rule that covers all of them. You just have to kind of practice and get used to, for this particular integral, what feels like it'll be useful. So, you know, but with a little bit of practice, you get used to the idea of, here's a thing worth trying. Let the variable be the denominator, see what happens, see if you can get that to work out. In this case, it does. Don't forget your absolute value when you do the natural log. Don't forget to change back to the original variable you have at the end. Remember to try to simplify as much as you can. So for example, if instead of z cubed, this had been a z squared plus 1 in here, well, z squared plus 1 would always be a positive number as long as z is real. So then the absolute values could be demoted to just parentheses, and that would be a simpler form, and that would be good to do. But here, z cubed plus 1 could be negative, so we can't simplify this any further. This is as simple as this gets. One last example, let's take a look at number 50 from the textbook. We have the integral of x over 1 plus x to the fourth dx. Let's try that guideline I suggested where we let the denominator be our variable. We have u equals 1 plus x to the fourth. Then for du, we get 4x cubed dx. The 4 doesn't matter, that's just a scaling constant. We have an x cubed dx, and we look here, and we don't have an x cubed, do we? If this were an x cubed in the numerator, this would be perfect. But it's not. There isn't really a good way of algebraically rearranging these things. So this is not a useful substitution. We could try see if we could do some algebraic rearrangements, but this 1 plus x to the fourth, that's not an easy thing to factor. I mean, it technically does have to factor, but it would factor into two irreducible quadratics that are unpleasant. So we might be a little bit stuck there for a moment. Again, as I said, integration is sometimes a bit more of an art than a science, and we want to think about, you know, what kind of patterns this might resemble. Ignoring the x for a moment, this denominator of 1 plus x to the fourth, we have 1 plus, and that x to the fourth. Now, 1 plus x to the fourth isn't exactly a pattern that you are expected to know, but x to the fourth is a perfect square, right? And 1 plus something squared in a denominator should feel kind of familiar. So if we do this manipulation first, and then we say, okay, let's take u equal to, this innermost thing is an x squared. If u equals x squared, du equals 2x dx. And we do have an x floating around, don't we? That means that a half du is equal to x dx. So this integral that we have is equal to, we can have a half out front, is an integral of 1 over 1 plus u squared du. Or we could just put this as du over 1 plus u squared. But here I wanted to pull this out to make it a little bit easier to see what's happening here. 1 over 1 plus u squared is a derivative of a known function, right? Its antiderivative is the arctangent of u. So we have 1/2 the inverse tangent, or the arctangent, of u we said was x squared. So that's an x squared. If you want to make that a little bit easier to read, I suppose you could put that in parentheses, plus a constant. Okay. So that's something to look out for here is if you have a constant plus some perfect square, even if it's not x squared, if it's just some perfect square, you might consider whether a substitution could be a path to an arctangent as an antiderivative. But, you know, that's kind of how that one works out there. Like I said, you just kind of have to see a bunch of these examples, learn some of the little tricks and techniques that show up. Practice these. You'll accumulate a kind of a toolbox of techniques you can apply, and just get used to their applications. Definitely make sure you do enough problems to get used to how substitution works, This is something that even if you look at the problems and say, oh yeah, that makes sense, I'm speaking from experience here, if you don't actually do it, it becomes difficult to apply. So make sure you give those a try, but this is the basic idea of how we apply substitution in some of the simplest cases to indefinite integrals.